In standard computer vision, we usually ask a model to look at an image and tell us, what is this? That's classification. The output is a single label. That semantic segmentation, or dense prediction, is structurally different. We aren't asking for one label, we are asking for a label for every single pixel. If you have a standard 1080p image, you don't need one answer, you need 2 million answers. And yet, for years, the state-of-the-art models for this dense task were just hacked versions of classification networks. They were built to summarize, not to detail, and that creates a fundamental structural conflict. To understand why this is a problem, we have to talk about receptive fields. To know that a gray patch of pixels is part of a cat, the network needs to see the ears, the tail, the whiskers. It needs context. In standard networks like VGG16, we get this context by pooling. We shrink the image. We downsample. By the time you reach the deeper layers, the image is 32 times smaller. You have great context. You know it's a cat. But you've lost the resolution. You don't know exactly where the cat's paw ends and the grass begins. Previous attempts tried to fix this by upsampling, basically trying to guess the missing pixels. But what if we didn't have to shrink the image in the first place? This brings us to the core innovation of the paper, the dilated convolution. Let's look at the math. A standard discrete convolution uses a filter, say 3 by 3, and slides it over adjacent pixels. This is a dilation factor of 1. But the authors modify the operator. They introduce a dilation factor, L. If we set L to 2, we still use a 3 by 3 filter, but we insert gaps. We skip every other pixel. The filter now effectively covers a 7 by 7 area, but it still only has 9 parameters. It computes the same amount of math, but it sees a much wider area. Crucially, the authors clarify that they aren't constructing a sparse filter with zeros in it. They are modifying the way the operator accesses the data. Same parameters, wider reach. Here is why this changes everything. If you stack standard convolutions, your receptive field grows linearly. Layer 1 sees 3 by 3. Layer 2 sees 5 by 5. It's slow. But with dilated convolutions, we can increase the dilation factor exponentially at each layer. Layer 1, dilation 1. Layer 2, dilation 2. Layer 3, dilation 4. By the time you hit layer 4 with dilation 8, your network is seeing a massive chunk of the image, all while maintaining full pixel-perfect resolution. The authors call this exponential expansion. You get the global context of a pooling network with the sharp resolution of a raw image. No downsampling required. The authors package this logic into what they call the context module. It's a plug-and-play block designed to sit on top of an existing dense prediction network. It consists of 7 layers. The dilation factors follow a specific sequence: 1, 1, 2, 4, 8, 16, and finally 1. It takes feature maps as input and aggregates context from all these different scales. Note the numbers. By layer 6, with dilation 16, the network is aggregating information from a massive area. And because they strip out the pooling layers, the output has the exact same resolution as the input. It refines the prediction using global knowledge. But there was a catch. When the authors first tried to train this module using standard random initialization, it failed. It didn't improve accuracy. Why? Because you're inserting a complex random mathematical function into the middle of a network that's already trying to learn. It confuses the gradients. The solution was identity initialization. They set the filters so that initially, the module simply passes the signal through unchanged, like a clean window. This allows backpropagation to gradually learn the contextual features without shocking the network. It turns the module from a barrier into a transparent layer that slowly becomes intelligent. The context module needs a base to sit on. The authors adapted the VGG16 network, but they performed some aggressive surgery. They removed the last 2 pooling layers. These were vestigial components from the world of classification. But removing pooling changes the math for the subsequent layers. To compensate, they introduced dilation into the existing VGG layers, dilation factors of 2 and 4. This kept the pre-trained weights valid, but stopped the resolution from dropping further. They reduced the image shrinkage, so the output feature maps were 64 by 64, not tiny 7 by 7 grids. This front end alone achieved 71.3% mean IOU on the Pascal VOC test set, outperforming previous systems, even before adding the context module.
The paper Multi-Scale Context Aggregation by Dilated Convolutions proved a crucial point. We don't need to choose between resolution and context. We can have both. By replacing pooling with dilation, we expand our field of view exponentially while keeping our prediction dense. The authors showed that the vestigial structures of image classification, padding, pooling, downsampling, are not just unnecessary for segmentation, they are harmful. This paved the way for modern architectures that operate at high resolution from end to end, seeing the whole picture without losing sight of a single pixel.